All right, our functional limit definition turns out to be really useful in defining one of the central concepts in analysis, and that's continuity for a function f. Right, the way that we define f as continuous at a point c in its domain looks really similar to the functional definition of a limit. So for every epsilon bigger than 0, there's some delta bigger than 0, such that if I'm within delta of c, then f of x is within epsilon, now in this case of f of c. So the difference between this and the functional limit definition, right, is one, we drop the greater than 0 requirement, because for continuity we are concerned with what happens at c, and so we want to allow x to be able to be equal to c. And we want to show that under that condition, we can make f of x be within epsilon of the function value itself, so that the thing f of x is getting close to is what we want it to get close to, the value of the function at c. And kind of intuitively, this prevents things like holes and jumps and gaps in the graph. Now, we're not going to make a big issue of this. The definition for continuity allows c to be an isolated point of our domain. And what it ends up implying is that functions are continuous kind of automatically at any isolated point in a domain. Those are typically not that interesting for us. And so we're often thinking of c as being a limit point to the domain, in which case we get the sort of standard formulation from calculus that a function is continuous at c if the limit as x approaches c of f of x is the same as f of c. Right? So this is kind of how we think about continuity, really, but the definition has a couple of subtleties in it, even though we won't really discuss them very much at all past now. All right, so we're going to do one example with the definition. We're going to show that f of x equal 4x minus 2 is a continuous function at the point 3. So we need to show that the limit as x approaches 3 of 4x minus 2 is equal to what we would get if we plugged in 3, right? So this is 4 times 3 minus 2, and that's 10. So 12 minus 2 is 10. All right, so that's the target limit. That sort of takes the place of capital L from before. And so let's let epsilon be bigger than 0 and consider the thing we want to make small. So f of x minus f of c, 4x minus 2 minus 10. And the kind of hint that we're on the right case is if in doing our algebra we get x minus 3 to appear, because that's the thing we have control over. Right, well, I think that's going to happen because I get 4x minus 12 and so what I'm trying to arrange is for 4 times absolute value x minus 3 to be less than epsilon. Well, this happens whenever x minus 3 is less than epsilon over 4, and so that reveals the suitable choice for delta. And the rest is just, as usual, kind of fitting it into the formal statement of the definition. So let epsilon be bigger than 0, and take delta equal to epsilon over 4. Then, if x minus 3 is less than epsilon over 4, we have f of x f of 3, there should be an absolute value there, not a parenthesis. That's 4 times x minus 3, which is less than 4 times epsilon over 4, which is less than epsilon, equal to epsilon. So that should complete the proof.